Module 15. In this one here, we're going to be deciding, do I use a binomial distribution or do I use proportion? This is a little bit frustrating because the problems will look identical. And we're going to have to choose between the two. And they're not interchangeable. It comes down to the size of the sample you're working with. But I'll show you that. Okay, let's put up some. This comes right out of the textbook. I want to talk about this. Okay, a binomial experiment. Okay. This has to do, binomial means two, bi, okay? Two outcomes. We've got to be able to set it up as a dichotomy. This is a yes or no, a success or fail, pass, fail, or something like that. It's got to be only two choices for it. You're going to see this a lot when they're doing, what do you call it? Political polling and stuff. Do you favor somebody? Are you favor somebody for president, yes or no? Okay? Or do you recognize this name? Or does a tree have a certain disease? Is a woman pregnant, yes or no, or something like that? Okay? These are yes or no type things. Okay? This is not measuring the size of something. What it's looking at is out of 100 people, how many have this condition? Or out of, 3 million people, how many have this? Or what percent of the people has AIDS? Or something like that. This is what we're talking about. They either have it or don't have it. Okay. There must be a fixed number of trials. Each trial can have only two outcomes. Okay? The dichotomy. The outcomes of each trial must be independent of one another. In other words, whether somebody has it or doesn't have whatever you're measuring doesn't affect the other one. And the probability of success must not change. It must be the same for every trial. So, for example, if I flip a coin, there's a 50-50 chance of it. If I flip the coin 100 times, I would expect to get about 50 heads and about 50 tails. Okay? And this tells us what's the probability of getting 48 heads or 49 heads out of 100 or something like that. And we can either do it as the number of items out of the number we have, or we can divide them and come up with a proportion. So 48 heads out of 100 tosses would be a 0.48. Okay? This is what we're dealing with. Now, for notation in your book, okay? The probability of S and probability of S is probability of success or failure. Okay, we're not going to use that. We're going to use the little p and q. P is the success, q is the failure, and these two add up to be 1. What do I mean by that? If there's an 80% chance of somebody succeeding, that means there's a 20% chance they fail. If we ask how many people like strawberry ice cream and it's 40% of the population, that means 60% don't like strawberry ice cream. Okay? Now, we're going to use little n for the number of trials. And later on, I'll use capital N to refer to the population you're working with. Okay? This is the notation in the book. And here's your formula. Okay? N factorial, you start with n. So 10 factorial would be 10 times 9 times 8 times 7. Okay, this is your formula here. Nobody's ever going to use it. We got tables for this. Okay? Let me find the tables, and I put it up here. Just to get, these are in the back of the book. Okay. This is what it looks like. Let me bring that down. See, there's your formula up at the top. And you come down. See over here, you got an N and a K. All right. I'll bring another example up from your book. But if we flip the coin 3 times, you could have no heads, 1 head, 2 heads, 3 heads. Okay. If we shift over, way over to the right, here, 50%, there's a 0.1250 chance of getting no heads, 1 head, 2 heads, 3 heads. Okay? How do we read this? Let me give an example from the book. Too many papers around here. Okay, how's this? Okay, because it's important that you can read the table. You go to the left and you find n and you find how many. So if we're doing something 3 times, okay, right here, they've already calculated for you under the probability of success, 50%. You come down, this is the probability of none out of 3. So if I flipped a coin 3 times, probability of getting no heads would be 0.125, or 1 1/8, right? It's a 50-50 chance. A half times a half times a half is 1/8, or 0.5 times 0.5 times 0.5 gives me 0.125, right? 0.5 times 0.5 is 0.25 times 5 is 0.125. Okay, the chance of getting 1 head, I could have a head in the first one, the second one, the third. I got 3 ways of doing it out of 8, or 0.375. Probability of getting 2 heads is exactly the same. I could get a tail in the first one, a tail in the second, or a tail in the third. Probability of getting 3 heads is the same as the probability of getting none. You notice this is symmetric because it's the 50-50 one. Okay? That's how we read the table. So with the binomial distribution, you can just go look up the answer. They tell you the formula, but unless your mother raised a fool, you're never going to actually have to calculate it because you've got the tables to go look them up. Now, what does a problem look like? Could be, well, 40% of the people in Fort Kent like strawberry ice cream. If I picked 3 people in Fort Kent, what's the probability that more than 2 of them would like, or 2 or more would like strawberry ice cream? Okay, well, how would I do that? Let's put this thing up. Let's go play with the table. Okay, what have I got here? All right, I'm working in this. I said 3 people. I want 2 or more. So I'm going to take the values for this and add them up. But this is, I got to slide all the way across to 40%, right? Because I said that was the thing, 40% liked it. And in my 3s, this is the probability of none, 1, 2, and 3. So I would add these 2 together and get 35-2. Or it is a little bit more than a 35% chance that 2 or 3 of the people would say they preferred, out of 3 people, of getting that. Okay? The chances of getting 0 or 1 are right here, 21-6 and 43-2. Okay? So this is the probability of nobody liking it, of 1 liking it, of 2 liking it, of 3 liking it, out of 3 people. The next table down would be if I sampled 4. Here's my probabilities. So if we could set this up as a binomial thing, we just go look up the answer in the tables. Now, what happens if the number's bigger? Well, let's go back and let's look at it in terms of proportion. Okay. If P was the probability of success and Q was the probability of failure, we know that P equals 1 minus Q, and N is the number in the sample. Okay, where P is the number of successes divided by the number in the thing. Okay. Why do I care about this for proportion? The problems are going to be the same thing, except that when the number gets big enough, this is normally distributed. Okay? So if in the problem, if I'm talking about people in Fort Kent liking ice cream, if it's 40% that like it, if I go out and sample 100 people, okay, remember the formula? You'd have to, I don't have a table for 100. 40 out of 100, okay, would be a lot of work. And so what do? I say 40 out of 100 is 0.4. And I'm going to use this. This is normally distributed with P at the center with a standard deviation of P times Q divided by N. Take the square root of that. Okay? This is important because when I can set this up, I always have it normally distributed. Okay? This is normally distributed. It's centered around P as the mean, and it has this for a standard deviation. Now, if I'm working with the binomial distribution, let me put that up instead. I got that out of the book. This is what I'm going to have. My mean is n times p, and my standard deviation is the square root of npq. But if I'm going with the proportion, in other words, I'm using p, then I got to divide this by n, and this, the n cancels out. This becomes over here. If I'm working with p, this becomes square root of p times q over n. And the square root is taken after I do the division. Don't do it before. Okay, this is for proportion. Okay. Now, let me play a game here and do a quick little sample. Okay. If I have 100 people and a sample, and p equals 0.40, okay, what's the probability that I have 50 or more? Okay? How am I going to do this? 50 out of 100 is 0.50. Okay? This is my thing. So I've got a picture here. I'm centered at 0.40. 0.50 is somewhere up here. I want this number. Okay? How do I calculate this? I need to know what my standard deviation is. Standard deviation is going to be what? I have to take, let's slide it over here, p, q, divided by n, take the square root. So that's 0.4 times 0.6 divided by 100. Okay? Then take the square root. This is 0.24 divided by 100 is 0.024. Square root of that is about 0.49. Okay? Let's round it off to 0.5 just for this example. Everybody see what I did? Multiply p times q, divide by n, then take the square root. Okay, so I would take 50 minus 40 divided by 5. This is 10 over 5, or 2. I've got 2 standard deviations, okay? Now, let me go get my table. Where is my normal table? Here it is. Do I have 2 on here? No, I got to slide it up a little bit. Right there. I'll use this as my thing. Okay. 2 is 9772. Okay, everybody see that right there? Okay, so if I go back to, let's swap these around. Go back to this. This is 9772. That I am below this. Okay? So if I asked, what's the chances I got 50 or less? 9772. I'll get that down a little too far. Okay? What's the chances I'm above that? Remember, this all adds up to be 100%. So I take 1.000 and I subtract 9772 from that and get 0.228. So it's about a 2.25% chance that I would get 50 or more people saying they liked strawberry ice cream if, in fact, 40% of the people in the population did. Okay? We can go over this again. So this is the P from the thing. This is what happened from my test, or what they're asking about. I subtract these and I divide by my standard deviation. And I calculated my standard deviation as approximately 0.5. Okay? I did that over here by taking p times q divided by n and then take the square root. Okay? I cheated a little bit. It should have been 0.49. I could do this more accurately. Yeah. But the important thing is the process. As far as that, how do I do this? Let me back out on this a little bit. Okay, just to put it all together. That's what she looks like, and this is how it is. Now, so that would be how I calculate. Let's go through this again. I knew 40% of the population liked strawberry ice cream. I said the question was, if I sample 100 people, what's the chances that 50 or more will like it? 50 out of 100 is 0.50. This is going to be normally distributed. 40 is my center. 50 is over here somewhat. And I want more than that, so I'm looking for this number. If I said 50 or less, I would be looking at this. This is going to come straight out of the table. First thing I got to do is calculate the standard deviation. If P is 40%, Q has to be 60%. So this is 0.40 times 0.60, or 0.24. I divide by the size of my sample, 100. Okay, that gives me 0.024. Take the square root of that, I get 0.49. That's my standard deviation. Then I take my number minus my mean divided by my standard deviation. This gives me a z-value. This was 2.0 approximately. I go look that up in the table, and it gives me 9772. That's how many are 50 or less. If I want or more, I've got to subtract that from 1, and I get 0.0228. So my answer is about 2.28% is the chance that I would get 50 or more. Okay? Now, just to quickly go over how do we determine what happens. Okay, remember, this had to be a dichotomy. These problems are all going to look alike. Okay? And in general, these are the conditions to validly use proportion. You're going to try to use proportion all the time because it's the easiest one to work. We don't need to go through the things. If the number n is too small, then we go to the tables for the binomial tables. You don't want to try to calculate binomial by hand. Okay, 3 conditions. What are the conditions? The sample had to be a simple random sample. Secondly, the sample size, little n, cannot be more than 10% of the population size. So little n is less than or equal to 0.1 times capital N. It's a fancy thing. In other words, I can't sample more than 10% of the population. Why? That destroys the independence. And the 2 pieces that I cut, in the problem I said 50 out of 100 or 40 out of 100. The 2 pieces, n times p and n times q, both got to be 10 or more. In other words, I can't, if I'm only sampling 10 people, how can I break 10 up into 2 pieces that are both bigger than 10? This is why this does not work for small sample sizes, and I've got to go to the tables using the binomial tables. Okay? This is going to hang us up when we get to the fringes of the population. If I've got something that is like one single-digit thing, let's say I've got 2% of the population, doing name recognition, and we sample around the country, how many people, you know, have ever heard of Roger Roy and he's running for president, right? And you come down to, you know, nobody, less than 1%. Okay, if I sampled 100 people, 1% of 100 is 1. That invalidates this. In other words, I'd need a real big sample to try to calculate how accurately my name recognition was. Okay? So when you're down in the single, like the 1, 2, 3%, or up in the 97, 98, 99%, because it's got to work on both sides, the pieces you cut, n times p and n times q both have to be 10 or more. So if I'm dividing up 100, I can't have 98 and 2. I can have 75, 25, 90, 10. Okay, that's the smallest I can get. If it's going to be worse than that, I've got to get a bigger sample size. If I sampled 1,000 and I had roughly 10%, 10% of 1,000 is 100, I'm nowhere near the 10 number. Okay, this is what I'm saying. As the number gets bigger, this is more and more valid. But these are the 3 conditions that wipe out validity, that stop you from using proportions. You're going to see, and as we go through the course, proportions are going to be used. This is the basis for all your preference polling and stuff for politics, and you're going to see this used quite often. And in practice, this is really going to be, in the field work, this is about the only time you're really going to be sure that you've got a normally distributed population. We talk about normal all the time in the book, but when you get out into the real world, it's really hard to have a normally distributed population, so we have to make adjustments. This, if you can set it up like this, in terms of a dichotomy, and we go with proportions, then you deal with the normal distribution. Thank you.